So yeah, it's a pleasure to have Samir again.
Okay, so this is more like a seminar. So we had a nice bunch of questions during the previous colloquium, but today I would like to ask you to have even more questions than before. So essentially, the goal would be to really understand how Hawking radiation happens, and so till you completely understand it at the level of maybe an undergraduate calculation, you should not stop. We should keep going for more and more clarity, till we can completely understand where Hawking radiation comes from, and that is really the source of all the paradoxes. So I think I will do the following. I'll just review some slides we had last time so that we can get reoriented and connect to last time on what the Hawking puzzle was. And then we will go to the task for today, which is to understand Hawking radiation in full detail. Okay? And then if I have time, I will talk about this thing called a small corrections theorem, which tells you that Hawking's argument is actually completely rigorous. If somebody says there are small quantum gravity effects we have somehow not taken into account and maybe that will solve the problem, it's not like that. The argument is completely rigorous, and what the argument will prove is that if the horizon of a black hole is like basically a normal place like this room, it's empty space to leading order, there can again be small corrections. That's the point of the small corrections theorem. But to leading order, if it feels like an empty space like this room, then you cannot actually save quantum mechanics. So that's really a very strong statement then, because everybody does think, at least in classical and semi-classical physics, that the horizon of a black hole is empty. So this region, for somebody who's falling in, just looks like empty space. But if that is true, then you can rigorously show that there is no way that you can save quantum mechanics. That was Hawking's argument, and now it will become completely precise. And to do that, you should really understand where Hawking radiation comes from. And so most people actually have not worked through this calculation. Even people who work in this field in string theory these days have never actually gone and looked at Hawking's paper. We won't need to go and look at the paper. I will give you a simple toy model of undergraduate quantum mechanics involving coupled harmonic oscillators. If you solve that, all the essence of the calculation is there. So it's not like it's a toy model in the sense that with this there are many more concepts you need to understand Hawking. Everything that you have in the exact calculation of Hawking, if you solve this quantum mechanical problem, all the effects are here. Okay, so in that sense, that quantum mechanical problem we should all solve completely, and then we will understand what Hawking radiation is, and then we can understand the puzzles. Okay, so first I'm just going to recall some slides from the colloquium. So you have seen these before, but just to get oriented to what the problem is, you remember we talked about the fact that gravity is an attractive force. So if you put two particles close to each other, there's a negative gravitational PE. This particle has intrinsic energy mc square. So the total energy of this particle, when it is kept near a heavy particle, will have mc square, but also a negative term. So then if r becomes sufficiently small, the negative term becomes very negative, and the total E can actually become negative. And so that means that if you keep some particle inside this critical radius, if you use general relativity, instead of gm by c square, you only get an extra factor of 2. But then it's the same kind of idea. In there you get a particle with net negative energy, and that means the vacuum is not stable. If you can lower the energy of the vacuum by putting a particle there, total energy has gone down, then the vacuum is not stable. So that is the problem. Anytime you can create a sufficiently strong gravitational field, the vacuum is not stable. Okay?
Samir, since you're pitching this at an elementary level,
yes.
How would you, what argument would you make if, for example, for the hydrogen atom, I have a proton, but if I introduce an electron, then the energy is lower?
Yeah.
The hydrogen atom, quantum mechanically stable. So,
Yeah, I think there the point is that once you take all the quantum mechanical fluctuations into account, you can't really get an energy which is unbounded below. Because you can solve the hydrogen atom in the lowest energy state we know. It is something with a given energy, right? So why is the energy not lower than that? You think you can keep it closer to that, but the quantum mechanical, the kinetic part spreads you out, the potential part puts you in.
My question was how, when the hydrogen atom comes to one's mind when you give this
Yeah.
argument. So So what part of the argument, your argument would have to be
Yeah.
modified if one kept the hydrogen atom
Yeah.
sort of in your rear view mirror?
Yeah, so I think one interesting thing is that if you take classical electromagnetism, just classical theory first, you know there is a way to prove that the energy of any bunch of charges, both positive and negative, is actually always positive. So if you remember this calculation, it roughly goes like this. The total energy, let's call it U, is equal to integral of rho of x, phi of x, d3x. Right? People write this. And then you write your rho as minus the Laplacian of phi. Okay. Then you integrate it once by parts, and this whole thing becomes equal to the because grad phi is E, it becomes E mod square d3x. Right? So this you would have seen in recourse, and so for any charge distribution, the total energy is always positive. Okay. Now the funny thing is, what does this mean? Because clearly if you take an electron and the proton here, the potential energy between them is negative. But here I am trying to write the potential energy. Okay? So what goes wrong there? So what happens is that if you do this calculation, which shows you the total energy is positive, at the same time Q1, Q2 upon R square looks negative, the reason is that it all goes into the self energy of the particle. There's an infinite amount of electric field which is diverging near the point particle. So first you have to understand what you're going to do with that guy. And that drives you all the way into the theory of renormalization. And so when you put all that together, somehow the answer still comes out positive. But if you renormalize the bare mass to be negative, because completely the bare mass is minus infinity, the energy of the field is plus infinity. If you renormalize the bare mass to be negative, you would actually get a negative answer. Okay. So it's not like I'm giving you any very good answer, but what we are going to be working at is this level, where for electromagnetism it's clearly positive. And it's really as simple as this. But for gravity, there will be an extra sign change, and then the whole thing, the same calculation gives you negative. So, yeah. Okay, so here we had a picture in general relativity, and we said the light cones point inwards at the horizon. And here the light cones can allow you to go out, and we will make actually good use of this picture today. So the important thing is, inside the horizon, things are always falling in, right? Because there's light cone, and here they can be going out, and this boundary is what we call the horizon. So is everybody comfortable with this picture? You've seen this before? And then we recall the fact that in quantum mechanics there are always vacuum fluctuations. They don't last a very long time because of this conservation, but near the horizon, the total energy can be zero because this can be negative, this can be positive, and this particle pair does not have to annihilate. Then you get an actual what's called on-shell process, and these particles can keep getting created. The problem with that was that they are going to be in an entangled state. This can be electron, this can be positron, or it can be entangled the other way around. It could go other way around, so it's a superposition of two terms, and that is what is called an entangled state. So if you have this vacuum fluctuation near the horizon, then the particle outside is entangled with the particle inside. If the two states of the particles are just called 0 and 1 for simplicity, the outside particle is called B, the inside particle is called C. So then you have 0, 0 plus 1, 1, and that's an entangled state. And so the entanglement keeps rising. And so here is the B, the C, the two members of the pair, and you can see they are entangled. I just wrote the thing again. And in this case, because there are only two terms in the sum, the entanglement is called log 2. If there were 10 terms in the sum, it would be called log n. When you produce more pairs, what does the state look like? The first pair was C1 and B1. Then the B1 goes out, the C1 falls in. So you can see C1 is most inside, B1 is most outside. Then another pair will be created at the horizon, that is B2 and C2. So C1 will be entangled with B1, so I can write the state like this for this particular pair. C2 is entangled with B2, so I can write the state like this for this pair. And then if I had more pairs, I would keep writing the state like this. Does this make sense to everybody? Just 1 second. So if I had like one pair of electrons making a singlet, then another pair of electrons making a singlet, another pair making a singlet, I would have three factors. You know, when you have independent systems, you multiply the wave functions. So I'm multiplying the wave functions. This wave function for B1 and C1 is entangled like this. For B2 and C2, it's entangled like this. And now if you compute the entanglement entropy of this, they are completely independent systems. When you have independent system, the entanglement entropy just adds, just like any entropy. So this is log 2 This will give you log 2, and if you have n such pairs, you will get n log 2. If I had 3 pairs, I would get 3 log 2. Okay. You can also see that more directly, the total number of states of these guys. Can somebody just tell me how many states are possible for this pair of electrons here? Each one can be a 0 or a 1. So how many states over here? 4. 0, 0, 1, 1, 1, 0, 0, 1. Whatever state I choose here, this is the partner. So if this is 0 and 0, this will be 0 and 0, because that is how they are produced. B1 is same as C1 and B2 is same as C2. So you can take any of the 2 to the power 2. If there were like 3 guys there, there will be 2 to the power 3 states here. And for each of the 2 to the power 3 states, you get the same state on this side. So you have 2 to the power 3 terms being added. So it's log of 2 to the 3, which is 3 log 2. That's what I said, n log 2. Okay, so it's very directly, you should be able to practice this and actually work out the entanglements, but the state is just this. Let's take the question.
So does the gravitational field entanglement the particles?
Does the gravitational field? No, the gravitational field only creates the particles. How the particles are entangled is just what normal particles are. Because in electron, if you have in your hand, like in this room, there is some gravitational field. Gravitational field in the black hole is not any stronger. As we said, for a galactic-sized black hole, the same field as in this room. But if I ask you what is the spin of this particle, up or down, it doesn't depend to have anything to do with the gravitational field here. It still has 2 states. Yeah. Yes. Delta T? You mean the previous slide? This slide? Yeah. So I put it in this relation because the total energy of the pair was 0. This was negative, and so I can make this positive. Out of all the possible energies, I can arrange it to be 0. If I am negative, I can choose this guy to be positive by choosing it at a suitable separation.
But does this have anything to do with being at the horizon?
Yes, if there is no horizon, then the energy of each of the particles will be positive. Each is mc square. So then I can never get, then delta E is always positive. That's the kind of fluctuations you have in the room. And then delta T will be something small because the product has to be h bar or less. You need the net energy to be negative so that you can then pair it with something which is positive. Usually everything is positive. And then I will get 0, and then I can have infinity. Otherwise, fluctuations only last a short time. They are always there. We measure it in things like the lamp shift, but they don't do very much. They do what they do, but nothing very remarkable about it. Here there is something strange. So then we talked about entanglement. We got these states. And then we said the entanglement will keep growing. If I go through more and more steps, the entanglement is rising. So after 1 step it is log 2, after 2 steps it is 2 log 2, then 3 log 2. That is this graph. This graph is called the page curve. It is different from the page curve of a normal body. In a normal body, the particles are emitted, but they are not coming out of the vacuum. See, here they came out of empty space. So they were entangled with each other because vacuum has no quantum numbers. So if a pair of particles comes out, they have to be in the singlet. That's why they're entangled. If you're actually emitting something from a piece of coal, then in the beginning there may be a singlet because the atom may be singlet when it emits a particle. This may be spin up, leaving the atom spin down, and this will be spin down, leaving the atom spin up, so they may be entangled. So the graph in the beginning will go up the same way as here, but after some time this atom will also float out. Then these two will be entangled, but not entangled with anything behind. So if you compare the entanglement with what's been radiated with what is left behind, in the beginning it seems to go up, but after a while it actually comes down, and in the end when there's nothing left there, it comes down. That's very important. In the end, when the thing is gone, you should not be entangling with that because you can't entangle with the vacuum. The vacuum has only one state. So entangling means you have state 1 times state 1 prime plus state 2 times state 2 prime. You need to have many states there to entangle with it. If that has only a unique state, entanglement should come to 0. And here the problem is you get the vacuum and the black hole evaporates, but the entanglement is not 0. In fact, it is very big. And so then the question became, what happens when the black hole evaporates away? So we talked about a little bit last time. The Hawking said in 1975, the hole completely goes away. So you have the vacuum, becomes smaller, smaller. And so this radiation is highly entangled, but there's nothing to entangle with. And then this guy doesn't make a proper quantum state. You guys remember that from last time? If 2 electrons are entangled, that's okay. But if 1 electron vanishes from the universe, the remaining guy doesn't have any state because it was up. If the guy was down, it was down. If the guy was up, if the other guy doesn't exist, you don't know whether the guy is up or down. It doesn't have any state, so you violate quantum mechanics. So that was Hawking's conclusion. And so this gave us the information paradox. You start with a star with some state psi initial. You make the black hole, you make the entangled pairs, and the black hole vanishes. Now this thing doesn't have any state. In normal quantum theory, you have an initial state, you evolve it, you get a final state. That is not the case here. So even without knowing the Hamiltonian of full quantum gravity, Hawking said no Hamiltonian can describe quantum gravity because black holes will form and evaporate, so you're already finished. Don't even look for quantum mechanics if black holes can form in gravity. Yeah.
Can I ask a couple of basic questions? So the fact that you're considering maximally entangled state, is that can that be shown with a actual calculation, or is it just a sort of an approximation?
It's a toy model I made. But so it turns out that suppose I put some numbers here, instead of taking 0, 0 plus 1, 1, I can take 2 times this and 1 times this, okay. I can just change the coefficients. Instead of log 2, maybe I'll get 3/4 of log 2. It's completely irrelevant because the only thing we care about is the entanglement rising all the way to the end. What you actually get is you get a sum of terms. It goes on 0, 0, plus 1, 1, plus 2, 2, plus 3, 3. And the relative weights are actually thermal because it's a thermal partition function. But because if you look at particles whose energy is of the order of kT, each coefficient is of the order of 1, e to the minus 1, e to the minus 2. They all order 1. So the entire entanglement is order 1 when you do the actual state. So you might as well write this for simplicity.
And also when you do the page curve, you do it symmetrically, but that's also sort of a cartoon, or?
It's a cartoon. What Page actually showed was that if you have a system, it first goes up in a straight line, very close to approximation, very close to a straight line, then comes down very close to a straight line. It turns over exactly at the place where the system reaches half its size, because if you have two systems, the entanglement is given by the size of the smaller system. You can't ever entangle by bigger than the number of bits you have. So at some point, this guy is going to become bigger than that one. And then the entanglement will be, instead of the dimension of that, it will become the dimension of this. So that was all trivial and known to everybody, because that's common sense. What Page did was he computed the rounding at the top. And he showed that if the size of the systems is m and n, then the correction there is of the last few bits is m over 2n. So he actually computed the rounding of this. And it's just of the order of 1 or 2 bits. So if m is like 20 bits and m is like 21 bits, then there's a small correction if they're almost equal. That was the only point of Page's paper. Otherwise, everything is actually obvious. And that's also a straightforward calculation, but it's just quantum mechanics. Okay, so that's where we were last time. So is everybody happy with the paradox? If we create the pairs, we have a problem. So what do we really want to learn now? So far, it was very schematic. If you have a vacuum, you have negative energy, so quantum mechanics, fluctuations, you get the pair. But now our goal is to understand that very, very clearly. How is the pairs actually coming? We actually want to understand what Hawking really did in 1975. So it should be so clear to us that we can convince ourselves and anybody else we are talking to that yes, if the horizon is a smooth place, you have to get this pair creation. Okay, you should be completely clear of that, and it should only require undergraduate quantum mechanics. So that's what we are going to do. So let's get a little bit set up on the whole thing. So one question people even asked last time, somebody asked that in the lecture, where do these guys go when they go inside? Like after some time it looks like they will fill up this region, and then after that if this thing goes clogged up, then this region won't be the vacuum, and then maybe the argument doesn't look like the same as before. So where do these guys go? Let's even ask about that. Okay, so could it be that after some point this hole fills up and then you can't create any more particles? From the picture, it certainly looks like it. But it is not like that. So now let's go to the metric of the black hole. So we will not use much of general relativity here. We will only use this metric at 1 or 2 points. And after that, we won't even use this. So this is the metric of the black hole. So there's a dt square term with a minus sign, a dr square with a plus sign, and this is the angular part. So can I ask if people are familiar with the Schwarzschild metric? Can I assume that everybody knows this? And even if you don't know, it's not a big deal. We won't use it after we say a few basic things. But right now, I'm going to use it for this slide. And the crucial property about the black hole is this metric. Do you think this is time independent? Is it a time independent metric? Yes. It looks like it. But the answer is no. The reason it's not time independent is it actually fails at r equals 2m. It only works for r bigger than 2m. So we have to actually cover what's called a complete Cauchy slice. If you can keep going somewhere else, you have to include that in your space. So this covers the space outside the horizon r bigger than 2m, but we have to also cover the inside. So we have to use some other coordinates which cover also the inside. But as we will see in a minute, there is no coordinate system which covers everything in which the metric can be time independent. So that's very important. The black hole is not actually time independent, because if you try to cover everything, it will never be time independent. So why is that very important? Suppose you could cover everything, and suppose the metric was time independent in that coordinates. Then in those coordinates, you can choose the lowest energy state on that particular slice. There will always be a lowest energy state. Now everything is time independent, so the state will not change. There will be no evaporation, no particles coming out, nothing. It will just stay where it is. So you can already see that it must be impossible to choose covering everything and also keeping it time independent. Okay, so it's not like this for a star. For a star, if you can, the metric is also a little bit curved inside the star and all that, but it's time independent. Okay, a star radiates, but that's different. You can take a neutron star, it doesn't radiate. So you can have many metrics which are time independent, but it covers the outside of the neutron star, also the inside of the neutron star, no big deal. But because here the horizon forms, this metric doesn't cover the inside, and if you ever try to go to Kruskal coordinate something which does cover the inside, it will always be time dependent. Okay, so we've already seen that qualitatively. Now let's see practically what it means. So for r bigger than 2m, do you know what is a space-like surface which covers space and the normal direction is time? So normally a space-like surface in Minkowski space is t equal to constant. So that's a space-like surface, and we always give our data, initial data on a space-like surface. So for r bigger than 2m, we can take this to be the space-like surface. But look at this metric and tell me what is a space-like surface for r less than 2m. So between r equal to 0 and 2m inside the horizon from here to here. Now this coefficient is actually positive and this coefficient is actually negative. So t plays the role of space and r becomes time. This part doesn't change, but here these two switch range. So in that case, you can see a space-like surface is not t equal to constant, it is r equal to constant. So for example, if I take the surface r equal to m, it is a space-like surface. So what do space-like surfaces look like in the complete metric? They look like t equal to constant outside. This is the horizon. This is r equal to 0. I'm plotting r in this direction. This is actually Eddington-Finkelstein coordinates, but if you don't know about that, don't worry about it. Roughly speaking, time is going this way. So it's t equal to constant outside, but inside the horizon, it is r equal to constant. So now you can see what the different slices look like. You can, in general relativity, you can evolve the slices any crazy way you like. So what I will choose to do is, outside I will evolve them the normal way you go from one time to later time to later time, because we want to see time evolution. Inside, time evolution is actually this way. This is space. At time evolution means you go forward here, because r became time and t became space. But I don't want to go near r equal to 0, because why don't I want to go near r equal to 0? It's singular. If I go near a singularity, I won't know what to say. The whole beauty of Hawking's argument is that we'll be able to complete the entire calculation of the full evaporation of the black hole all the way almost to the end point without ever going to a region where the curvature is high. That is very important, because if the curvature high region had to be involved in the argument, nobody could make an argument, because then you could say something new happens there and we don't know what it is. Okay. So now what we'll make the slices like this, we'll make them come here, we'll hardly advance them here. I just separate them for convenience, but I don't have to advance it at all. I can always choose the same line if I want. Don't advance it on this side, and on this side I'll keep advancing it, and this whole thing is actually a space-like surface. If you want the actual shape of this, you can find it in my papers, you can write it. It's a completely smooth space-like slice. Okay, so it's very funny. One side is not increasing, the other side is increasing. Now in Minkowski space you can't do that. In the beginning it seems you can do that. This is a space-like slice in Minkowski space. Can I advance it to the right and not advance it to the left? Can I make a slice like this? It looks okay. You can advance it more on one side, less on the other. There's nothing wrong with that. But see, if I keep doing that, after some time, what has happened here? What is the slope of this line? It's 45 degrees at some point. And then this line, is it space-like? No, now it is null. And if I advance it even more and not on the other side, then this line is not space-like. You can see it's become time-like. So you can only go a little bit, and after that you can't go anymore. So we can advance a little bit more here, a little bit less here, but can't do too much. Only a little bit you can do that. But in the black hole, this will keep going on, because you can keep making this up and up and up as much as you want. And on this side, you won't advance it at all. You can actually all make it the same line. This is the feature of the black hole metric that leads to all the properties of the black hole as being different from a star. A star will be more like this. You can advance both sides or advance one and not the other, but soon you have to advance the other side also. Otherwise, it won't be space-like. And here, the slices you can see are not the same as each other. This one is like this. This one is longer. Can you see that it is stretching? So later slices are longer. So it's like an expanding cosmology. It's just like keeps expanding and stretching, even though the black hole looked like it was time independent. It's not time independent. It's as bad as the cosmology, which is not time independent. Everything is stretching. But here also, if you include both the inside and the outside, any metric slicing, any slicing you make of this metric will always be time. The slices can't be the same as each other. Later slices are longer than the previous slices. So if you have the vacuum on the initial slice, that state need not be the vacuum on the later slice, because the metric has changed, it has stretched. And that difference between there will be some other state which is lowest energy on this slice. It's not the state which was lowest energy on this slice, and so the vacuum doesn't go to the vacuum, it goes to the vacuum plus stuff. And that stuff is the new particle pair. So even qualitatively we can see why the effect will come for the black hole, but here it's important there's an infinite amount of space inside the hole, because I can make this line as long as I want. You'll see in a minute, the hole therefore doesn't get choked up, there's infinite amount of space in here. Now we have to go and learn a little bit about quantum field theory, okay, but in a very, very elementary way. So maybe I can first ask how many of you here have taken some course in quantum field theory? Okay, so that's pretty much everybody, or you at least know what it is. Yeah. So let's just assume that you have heard about quantum field theory and just talk about a few basic properties, because that is what Hawking used. So what's the idea of quantum field theory? So suppose you have a scalar field. So let's take phi, which is a scalar field. I'll try to write it a little bit on the board and then go back to the pictures, because I couldn't write all those things in the pictures. So you have a scalar field. So what is the Lagrangian for a scalar field? The Lagrangian is d mu phi, actually with a minus a half if you like. And then if it's a massive field, you will write a half m square phi square is also a minus. Are people familiar with the scalar field? Is that okay? I write that? Okay. So let's be even more explicit. So the Lagrangian is equal to a half phi dot square minus a half. Then this is grad phi square. If you just expand this with the correct metric, and then you have a minus a half m square phi square. Okay. And then if I want the action, I have to integrate the Lagrangian over all space and time. I get the action. Okay. From this I can compute the Hamiltonian. So the Hamiltonian is a half phi dot square plus a half grad phi square plus a half m square phi square, but then I should integrate this over all space. This was a Lagrangian density. If I integrate this over all space, let me just take one dimension. If it was 3-dimensional, I would write d3x. One dimension, I just write dx. Can people still see in that corner, or is it blocked by the lectern? Last line is not clear? Half of it. Okay, so I'll write there now, but here I have just written plus half m square phi square, and then there is dx. Okay, so suppose you had to put this Hamiltonian in the computer. Let us see what kind of terms are here. You can take your one-dimensional line and you can break it up into discrete points, because in a computer you always have to discretize everything. So that is my x line. Time will be going there. I can take a bunch of points, and at each point I have a variable phi. So I can call the variable here phi 1, phi 2, phi 3. I have a real number variable at each point. And then I can just see what the Hamiltonian is. The Hamiltonian is a half phi 1 dot square plus a half phi 2 dot square, and so on, because that is the kinetic term. If I take a half phi dot square at each point and I integrate it, do people agree that's what I have? Then I have a half grad phi square. Let me first write the last term. That is a half m square phi 1 square plus a half m square phi 2 square, and so on. So already at this point you can see, if I look at this Hamiltonian, if I take this term and this term, which both involve phi 1, this is the Hamiltonian of what? One of the students should just tell me. This is the Hamiltonian for? It's a harmonic oscillator. So I just have an independent harmonic oscillator at every point. I just haven't done the middle term, which I will do, but that's what I have drawn here. At every point I have a harmonic oscillator potential. Okay. And then if I look at this term, the grad phi square, how will I write that? The grad phi square term will be plus 1/2. Grad phi will be, for example, phi 2 minus phi 1, the whole square. Okay, divide by the separation epsilon, but okay, let me just take the separation to be 1, but it's something like a half phi 2 minus phi 1 whole square. Okay, so that's the gradient term. So these harmonic oscillators are coupled. Can people see that this couples the two oscillators together? Because there's one term phi 1 square, the one term phi 2 square. That's just like adding a little bit more here. But then there's a cross term phi 1, phi 2. That means the two harmonic oscillators are coupled. So I just drew that by the dashed line. So you can roughly think of this. Each harmonic oscillator is the same as a mass coupled to a spring. You know, that gives the harmonic oscillator. Just a pictorial representation. So masses coupled to springs at every point, and then you can join these by other springs, so that, you know, if they are different distances, they stretch and so on. And then if you just take springs with masses and then they are also, you join them by other springs, that's exactly what a scalar field is. So maybe you learned that when you were learning quantum field theory, that this Lagrangian is basically just reproduced by a bunch of balls attached to springs, and then if you shake the ball here, it will shake the other balls and so on, and that's the propagation of waves in the scalar field and so on. So I'm just probably telling you things you know very well, but I just want to remind you that quantum field theory is nothing more than thinking of something like a scalar field in terms of a bunch of harmonic oscillators. The only last part we need to know about this, so at each point of space there's a harmonic oscillator. Remember, that's what I said here. The oscillators are coupled. So if you excite this oscillator, it will actually, if they were not coupled, exciting this guy won't excite these guys. But now because they are coupled, if you excite this, the wave will spread. That's how particles move. And then the only thing we need to know is what's the meaning of exciting, let's say, this harmonic oscillator. If it's in the vacuum, you say there is nothing there. If you put one excitation, it means there's one particle there. If you go to second level of this, then it means there are two particles there. So that's the meaning of quantum field theory. You define the number of particles at a position by saying which state of the harmonic oscillator you are in. And so you are coupled. Because they are coupled, you can actually diagonalize it to momentum basis, and then you can take the ground state of the coupled oscillators. So if you learn quantum field theory, you will know what to do that. And then each of the momentum waves, which are the actual eigenstates of the problem, they'll give you a particle of momentum k. But let's not worry about that. Roughly speaking, if you excite the oscillator here, you have a particle here. If you excite the oscillator here, you have a particle here. And because they are coupled, if you start with a particle here, it can move here or to the left. And that's all there is to quantum field theory. Okay? So quantum field theory is just the quantum mechanics of many harmonic oscillators which are joined together, and there is nothing deeper than that. Okay? So once we understand what particles are, this is all that a particle is, now we can ask how a particle can be created. Okay? So if you are in the normal vacuum, you start with all these springs and you don't excite any of these oscillators. You go to the ground state of the coupled system. If you leave it there, it will always stay there. So you have empty room, it will stay empty. But now what are we going to do? If the metric is changing, then I am somehow changing these oscillators. Maybe I am changing the separation between them. If I, let's say, make the separation very big, maybe the interaction between them will go away. Okay, they can't interact anymore. So you can see what will happen. Suppose I had two oscillators which were interacting. Then the ground state of the two coupled oscillators, do you think it is the same as the ground state of the first one times the ground state of the second one, or do you think it is something different? It's a very elementary question. I'm just tricking you by asking it. You probably know the answer. So what will be the ground state if I have two oscillators and I couple them? Is the ground state of the full system going to be the ground state of first times the ground state of second? No. It's going to be something else. If I decouple them, then what will be the ground state? Vacuum of this, lowest state of this times lowest state of this. This is all that you need to know. Because this is what will happen. I will start with a situation where they are coupled, and then as the space expands, the coupling between them will weaken. For a simple model, you can just say it's gone away. I will start with some particular state of the oscillators, but after I change the coupling, I will be in some other state of the oscillators. If I just look at what the change is, you will see I have produced particles. And that is all there is to particle production. This is all that Hawking did, and Hawking of course did it properly. He didn't discretize it or something, he just took the continuous fields and so on. But all that, if you do, it adds absolutely zero to the calculation. Everything we want will come from here. So now let us see what's going to happen. So let's just take two oscillators, and we will see why this is relevant to the Hawking problem. But this is a toy quantum mechanics problem, which I will encourage all of you to go home and try to solve. Okay? So take two oscillators like this, and they are coupled. So two oscillators coupled to each other, and the vacuum of this entire system is the ground state of the coupled system. So do you think, you guys, if you go home, you could work out for me the ground state of two coupled oscillators? This is Lagrangian, this, and one coupling. Do you know how to solve that? You first diagonalize the Hamiltonian, and then you get two separate oscillators. Then you solve them, and then because you separate the oscillators, the wave function is the product. When you go back to original variable, this is not a product. Okay, but you know how to solve it. And I have some lecture notes on the web. If you want to see the solution, you can go and see it. Okay, and now suppose somebody stretches the space, then the oscillators go away from each other. The coupling becomes weaker, but just because we are understanding everything qualitatively, let's say the coupling goes to zero. Okay, so now let's see what will happen. Now there are two ways I can change this coupling. Either I can change it very slowly, that's called adiabatic. If I change it adiabatically, do you guys know what will happen? If I start with a coupled pair of things and I'm in the ground state of the coupled system, I told you I want to start in the ground state of the coupled system. If I adiabatically remove the coupling, very gently I remove the coupling down to zero, do you think I'll come down to the ground state of the two uncoupled oscillators? Okay, so something very interesting. There's something called the adiabatic theorem. Have you guys heard the word the adiabatic theorem? So the adiabatic theorem tells you that if you are in the ground state, in particular, and you slowly change the Hamiltonian, then you will end up in the ground state of the new Hamiltonian. Okay. So this time it will be rather boring. I start with the ground state of this. If I change the coupling slowly, I will actually end up in ground state of this times the ground state of this. Okay. But I don't want to do it adiabatically. I'm going to do it quickly. What's the limit of quickly? Quickly compared to what? If the frequency oscillator is, let's say, 1 second, the period is 1 second. If I do it over 100 seconds, it's adiabatic. If I do it in 0.1 second, it's quickly. Okay, there are just two possibilities, just compared to that 1 second. So let's do it completely quickly. So I'll just do it at 0 time immediately. If you just change this is the potential has changed because this term was there, and now this term is not there. I changed the Hamiltonian. So another quantum mechanics question to you. If you suddenly change the Hamiltonian of a system from H1 to H2, does the wave function suddenly change from some psi1 to some other psi2, or does the wave function stay constant? Stay constant. Wave function doesn't change suddenly because the Schrodinger equation says del psi by del t equal to something, but del psi by del t is a finite number, it can't suddenly jump. Okay. So in the sudden approximation, at least it's very clear, the wave function will remain whatever it is. And so now I know the wave function of this situation, but you already know it's not the wave function of vacuum times vacuum, it's going to be something else. So you can work out this problem, and you will find if you do this in terms of two uncoupled oscillators, we call this one B and this one B and this one C. You can see I'm coming back close to the Hawking problem in a minute. It will not be vacuum of each other. If it was adiabatic and done slowly, you will really get the vacuum this time, the vacuum of this. You get a little bit of 1 and 1, a little bit of 2 and 2. That's why I wrote the dot, dot, dot. Okay, so very simple quantum mechanical problem. You can go and work it out yourself at home, but this is all you need to do for Hawking's calculation, and this is all that Hawking really did. And there's nothing missing between this and the actual calculation of Hawking radiation. This is actually all there is. We'll call this oscillator as the part outside the hole, this oscillator as the part inside the hole. This is the particle production. So the only thing we need to go back and see is, in the geometry of the black hole, do you really see 2 points which are being separated from each other? That's what we are looking for. If there are 2 points being separate from each other, the oscillator here describes particles here, oscillator here describes particles here. They were coupled because they were close, so this was the Hamiltonian, and if they got separated in the process of black hole, the time dependent metric, then they got uncoupled like this, and the state, if it was the ground state here, now it will become a state like this, and you can see there are particles here. There's some probability there are no particles excited, some probability there's 1 particle here, 1 particle here, some probability there's 2 particles here, 2 particles here, 1 and 1, 2 and 2, but it's at least not the vacuum of this and vacuum of this. That's particle creation. You can also see that it is entangled. Okay. You also get 1, 0. It just doesn't. So actually, let me go back and see. In this particular case, you don't actually get 1, 0. It's just the even and odd parts. So for example, if you just had one harmonic oscillator and you suddenly change the potential, the parity symmetry is not broken. And if you don't break the parity symmetry, you get the vacuum, then you get 2 and you get 4 and you get 6. You don't get the odd states. So it is just a triviality. If you just do it slightly differently, you may even get to 0, 1. I don't actually remember, but the whole solution of this in some lecture notes. You can do that. The only thing, it is just entangled between the two, and that's all that matters. So very good question. If you slightly change the picture, you can even get 0, 1. Because this is a toy model, you're welcome to make that change. In this case, I think the parity symmetry prevents you getting 0, 1. So now we'll go back to the black hole. You remember the picture of the horizon. Outside, the light cones were like this. You can both go in and you can go out. As you come in, the light cones tilt inwards. So you can still go out and you can still go in, but a little easier to go in, a little harder to go out. Can you see that? It's harder to go out. And that's the effect of the gravity of the black hole. It's more difficult to go out. Once you go at the horizon, you can of course go in, but if you try to fly out, you just stay at the horizon. It's like you're trying to race out, but you're also being dragged in, so you stay at the horizon. And once you're inside the horizon, you can go in here or you can go in slowly, you can go in fast, but you can't even stay at one place because that is already moving faster than the speed of light. You have to keep going in. So now let's see, if I draw the horizon here, same picture, look at the outward going light ray, somebody who's trying to escape. If he's outside, it's difficult to escape from near the horizon like here, but as you go further out, you can escape, and ultimately you go out and then you can keep going at the speed of light out here at 45 degrees. So this is a null geodesic going out, which started outside the horizon. The null geodesic goes like this. Is everybody comfortable with that? It's very simple. You'll take the metric of the black hole, you can even calculate this in one line. A null geodesic, radial, just going outwards. If the same geodesic is still trying to go outwards, I'm not looking at the inward part, I'm looking at the outward part. You agree this should be called outward because it's trying to go out, even though it's not actually getting out. If I try to follow this guy, you can see it's here, then it goes here, because once you go further inside, see, it has to go in. It's further inside compared to this. See, it's further deeper inside. Then the light cone is even more tilted, so it goes here. So that geodesic will start like this and go here. If you're at the horizon, you will always stay there. So do people agree to these three paths? And so now you can see what is happening. If you take a little bit of space like slice here, there's an oscillator here, there's an oscillator here. They are coupled and they are at this separation. After some time, they are at this separation. After some time, they are at this separation. Can you see that they are spreading away from each other? So the whole beauty of a horizon is that it separates things like this. Okay, so now can you see that if I call the oscillator here as B and here as C, it's exactly what I had on the previous slide. B and C, in the beginning they were close, so they were coupled. Later they are far, so they are uncoupled. So if I start with the vacuum here, which is what I had, because in the beginning I just had empty space around the horizon. But after it evolves for a little while, there's some property empty and empty. There's some property, there's one particle here, one particle here. There's some property of two particles here, two particles here. But this is everything. What happened to the adiabatic story? Is it really changing fast or slow? On the previous one, I just said, okay, we'll assume it changes fast, because if it changes slowly, then you will really end up at the new ground state. But here, now I can think of oscillators of all different frequencies. In quantum field theory, you have all different frequencies. High frequency oscillator means high energy particles, and low frequency one means low energy particles. So you can see that roughly the metric here, if you go back to the metric we wrote in the beginning, the metric is changing on the time scale, which is the crossing radius of the black hole, the 3 kilometer or whatever for a black hole. So that's the time scale. So all the frequencies of oscillators, which are very high frequency, whose wavelength is not 3 kilometers, but let's say 1 millimeter. Those are very high frequencies. For those, this changing over a 3 kilometer time scale is too slow. It's adiabatic. So those guys will not be pair created. They will just go back to the vacuum and vacuum. Nothing will happen. But
it's in this joy model that you had, I'm trying to understand. It feels to me that somehow the vacuum, which vacuum we are working with, that information is not going in.
so it is, yes, very important. It should go in. And it's going in the fact that when I started with this, I said I have the vacuum of the coupled pair of oscillators. Right? That's the same as saying I want the vacuum on this slice here. This slice is straddling the horizon. It's going from one side of the horizon to the other. So if I go back to my earlier pictures, this is the smooth vacuum in this slicing, which is the crustal coordinates. Right? I'm going smoothly across the horizon. So if I take a vacuum, which is the normal vacuum in the local flat space patch here connecting the two sides, that is the Unruh vacuum, or any vacuum with a smooth horizon to leading order will look like that. Right? So that is where the input has gone. I have used both sides of the horizon, and I've assumed it's completely normal flat space physics there, and that's why I have been able to write it like two oscillators, even though one was on one side, one was on the other, and that's where the input is.
So from your point of view, these three different choices of vacuum are the same. So
At this order, Unruh and Hartle-Hawking will both Hawking radiate, right?
Yeah,
that's true.
But for instance, Boulevard will be different.
So Boulevard will be different, because in Boulevard there's a singularity, so this guy is there, but this oscillator doesn't even exist. Right? In Boulevard, the inside is already a singularity. So assuming that you have this one and this one coupled like a vacuum, and you choose the vacuum state across the horizon, that step is false for Boulevard. So I've already put in the smooth horizon. Right? So that's our whole point. If the horizon is smooth, which is what happens in the classical picture, because we saw everything get sucked in by the light cone structure, and so that's very important. This was the whole reason we recalled the story from last time, that if we draw the whole picture, everything gets sucked in, so this becomes empty space. If this becomes empty space, then you can have this geodesic going out, geodesic going in. That picture of geodesics I just took from here, right? The light cones are used for these light cones. So it's very important that here I get the vacuum, because everything gets sucked in. So if this classical picture is true, then this is the vacuum. If this is true, then everything I have been saying right now is true. The slices look like this, they are smooth across the horizon. Then I have the vacuum here, it breaks here, I get the pair creation, because these are my geodesics. This is the complete story. So now you can see the story is so simple. There's almost nothing you can do to change the story. All that Hawking did, of course, was like a technical paper, so you'll actually write the full Fourier mode. We said there's one oscillator here, but really the oscillators are all the way here, coupled to each other, making a chain like this. But you're interested in waves of a wavelength of the order of 3 kilometers. So you can just look at one oscillator of radius 3 kilometers here, and radius 3 kilometers here, and just deal with that. The other modes don't do much. But if you want to keep track of all the modes and do it properly, that's the only thing which Hawking did. But it doesn't matter, as we said, the modes which have frequency wavelength much shorter than the scale, the radius of the horizon, they adiabatically change. So there's no creation for them. The ones with wavelength of the order of 3 kilometers, for them the change is sharp, it's not adiabatic, and then you get the pair creation. Wavelength longer than 3 kilometers, well, they don't even fit here. So somehow they are not relevant if you're working in a physics of radius 3 kilometers. So the entire physics is here, and so Hawking goes and finds this. So now we can put it schematically. Now that we've seen where they come from, this is the initial matter which made the black hole. Something falls into makes the black hole. We won't worry about it, but something had to fall in to make the black hole. But then if you had the vacuum on this, we said after the black hole is made, there's a vacuum around the horizon because everything goes in. So there's the vacuum on this slice. But the vacuum on this slice means this oscillator is coupled to this oscillator. They are both in the ground state of the coupled system. But when that evolves to the next slice, a pair of particles will be created. The particle B here, the particle C here, and they are entangled in this way. It's 0B, 0C plus 1B, 1C. But now that we know what we're talking about, I won't always take the trouble to write that. But you agree that these are two entangled particles. And then as you do the evolution, you can see what happens. This part of the metric was stretching. We saw that this part stretches. So this particle falls back here. This particle goes further out. We saw this geodesics were going out, so that guy goes out. This guy, we saw the geodesics were going in, so that guy goes in. This area is empty again, and so a new pair is created here. This guy is entangled with this guy. This guy is entangled with this guy, and those are the thing we wrote. This is the first pair, B1C1, entanglement log 2. Sorry, this is B1C1, entanglement log 2. This is the new pair, B2C2. At the next step, this will go in, this will go further in, this will go out, this will go out. New empty space here, a new pair comes in between. This is the entire process. Okay? So now you can see how simple it is. So firstly, the inside of the hole never gets filled up. The old particles just keep accumulating here. These guys go out, and here there's always extra space, and that's where the new pair is created, right? So the hole never fills up. But you can also see where the entanglement is coming from, and this picture is so robust because this is all low energy physics. When this particle separation of the two oscillators, let's say 1 meter, they're in the vacuum. By the time it becomes 3 kilometers, there's a pair. You only need the physics from 1 kilometer to 3 kilometer. These are wavelengths you have checked in the lab. Actually, this is radio frequency, so you know it inside out. There's no magic here, no quantum gravity, nothing, and you will keep getting the entanglement. Okay? Yes.
So we are looking into the vacuum around the horizon. So
yes.
In the previous slide, you drew some slices.
These slices.
How do we define these slices? Those slices, if it is space like outside, it will be tangling inside. So.
No. So these slices are drawn in these coordinates which I used here. Yeah. This, when I draw it like this, remember this slice is space-like everywhere. It looks like it is time-like here, but that's because the metric switch signs from space-like to time-like. You remember that story. But it's very important, if I draw a slice, it should always be space-like everywhere, otherwise not a slice. You can only give data on a space-like slice and then evolve in time. So that's very important. The whole structure of the black hole, let's go back to that slide where we started. What happened to that slide which had the metric? Yeah. So at r greater than 2m, t is time-like, r is space-like, and for r less than 2m, r equal to constant is space-like and t is time-like, and that's why we said this is a space-like slice. That's very important. So when I draw these points, this just looks bent, but this is really space-like. You can lay it out on a table, but really space-like. It just looks like that. That answers your question? Okay. Okay, so let's see if there are any more questions about this. So the whole point is that this is so transparent that doesn't matter how hard you look at it or any small modification you make to it, this will always keep happening because it's just quantum mechanics, right? And that's why for 40 years nobody could find any solution to the puzzle. And as you can see, anytime the horizon is a smooth thing, there's a horizon which just means light cones turn over and otherwise the thing is a vacuum, that's all we have used. If it's a vacuum, you have coupled oscillators in the ground state. If the horizon is there, they're going to separate. The ground state oscillator, when you decouple it, will create particles, and that's it. The entanglement, so entanglement is growing. So what step of this could you possibly change? And so the only thing that people could think about at that time was, one possibility is that this is all a leading order effect, but maybe there are some small corrections to it, and maybe they will help us. So I'm going to talk about that now. The answer will be that small corrections will actually not help us. But it was such a major confusion in the field that it drove the field for a few years in between there, and to some extent this is also the source of a lot of confusion going around today. Okay? So we really need to understand this issue. What can the small corrections do and not do? Because many major people in the field had this confusion. Okay, so I want to tell you about that, but let me just pause here to see if people have any questions about the Hawking radiation process itself. Yes?
Yes,
Yes, that is 100% true. I haven't shown that, but that's a very slow process, but this line is slowly getting smaller. That is true. But I don't have to worry about it at this crude level because the horizon, let's say, is 3 kilometers. Each particle you emit has wavelength 3 kilometers, so you can imagine how small the energy is. So the energy is like even smaller than an EV, right? So micro EV. And so if you reduce the mass of the black hole from 10 to the 33 grams by a micro EV, nothing will happen. So the horizon radius will change by hardly anything. But yes, you should do it with the full geometry where the metric is slowly decreasing and the radius is decreasing. And by now people have done all that. So there is something called the RST model in 1+1 dimensions where we put the feedback in exactly and you solve the Hawking radiation with the exact feedback put in. So you can do simple 2D models where you can do everything exactly. You can actually solve it in closed form. So yes, in principle you should do that. In practice, it does not change any of the issues that you're going to create entangled pairs. That's the only issue we care about. But yes, we should do that. Okay, so let's talk about the issue of small corrections. So I'm almost at the end of my time. We have about 5 or 10 minutes.
I think usually it's 2:30 to 4.
Oh, it's 2:30 to 4.
That's what they do.
Okay. Is that okay with everybody? You guys can stay awake for half an hour more. Okay. Okay, so let's talk a little bit about it. We can at least discuss the issue. We can finish the details next time if we run out of time. So what did people say? People didn't want to get rid of any of the steps here. Everybody knew that the black hole forms classically, so they had the black hole. Everybody knows quantum mechanics is given by quantum field theory. This story, nobody can beat quantum field theory because we have tested so well in the lab. All the way to the LSC at high energies, everything works beautifully, so you can't change this story. So then you're stuck. So then what people were trying to do was, maybe the following might solve the problem. The actual evolution I wrote for the waves, I drew it by these red lines. Just saying that they're stretching, there's some modes, these waves, and the harmonic oscillators. But suppose there are some quantum gravity effects which we don't know yet. That's always possible. They can't be very large because otherwise the black hole would not look like what we think. They can be very large near the center where you have Planck curvature at the center, singularity. But they can't be very large at the horizon because we think that's an empty space like this room. But they can be small. So whatever change I have, I've tried to show you small changes here, just schematically. So that's always possible, right? Some quantum gravity effect. If Hawking thought the answer was the red line, the actual answer may be the blue line. Okay, so why does that matter? Very small corrections can come, but why should we care? The idea that people had was the total number of particle pairs we'll emit is actually very large. So how much is that? It's of the order of mass of the black hole in units of Planck mass squared. Okay, so black hole mass is like 10 to the 33 grams, solar mass. And then if you take 10 to the Planck mass, 10 to the minus 5 grams. So ratio is 10 to the 38. And you square that, it's 10 to the 74. So there are 10 to the 74 particles emitted by a black hole. Okay. So then what people were hoping was, suppose there was like a tiny correction, which is 10 to the minus 74 at each step. Now that's very small. But you're going to emit 10 to the 74 particles. So then maybe all the corrections, because the number of particles is so big, maybe once you do all the corrections, then Hawking's calculation may not have been right. Maybe when you compute the entanglement, all the corrections, the whole effect may change by order 1. So do you see the rough argument? The number of particles is so big, even if every particular pair, the pairs come out slowly. One pair comes out in the crossing time. The time takes like to go across. Then another particle starts and comes out. Then another particle comes out. It takes a long time. But the number of particles is so huge. So if every particle had a little bit of correlation with the other particles, then the state would be slightly different at every state. If they only like 10 particles, it can't make much of a difference, right? But if the correction was very small, maybe 10 to the minus 74, but there are 10 to the 74 particles involved, well, who knows what happens? So it's actually a logical thing to worry about. So maybe the net effect of all these small corrections might remove the entanglement. So let's see again schematically, mathematically what that means. So this was the picture we had, B1 and C1, they are entangled, they give you log 2. Then at next step we said B1 moves out, C1 falls in, and a new pair is created, B2 and C2. These two are entangled, these two are entangled. Here these were entangled in the previous step. The total wave function, there's the wave function of the matter which is far away. So the wave function on this slice, for example, this is a complete slice. Should write a wave function on a complete slice. I'm calling it capital psi. It is made of the wave function of the matter, then the wave function of the first pair, then the wave function of the second pair. So Hawking assumed everything was independent of everything else, right? This matter is sitting here doing nothing, just creates the metric. That this pair did its own stuff. That this pair came out later, is doing its own stuff. But there can be small correlation, right? There's some magical slight quantum gravity effect could affect this pair. Depending on what was sitting here, this could slightly change. That's not wrong. And maybe depending on what this pair did, this pair could slightly change. It's not that far away from it. Maybe they could slightly correlate. And so this was Hawking's state, just directly tensor them all as if one guy, nothing to do with the other guy, nothing to do with the initial matter. This is what Hawking assumed. Now let's see if we can mathematically write down what does it mean to say that they slightly influence each other. Let's try to write it down. So Hawking assumed they look like this. I'm restating the fact. And then if you make, let's say, a small correction to it, it could be that you have this plus a small number epsilon. Let me add the orthogonal state. I'm just giving a toy example of what this change would be. So that means epsilon is a small number, much less than 1. So it will basically still look like empty space around the horizon to leading order. But look, I have allowed you a small correction. You could put something else there if you want. But this means a slightly more than 50% chance of getting 0, 0, a slightly less than 50% chance of getting 1, 1. Is that clear to everybody? This is an example of a small correction. Okay. So then at the first step, suppose you just got this. Suppose Hawking was right about the first step. At the second step, let's try to correlate all the particles. Okay, so how do you correlate them? Suppose the first step you got 0, 0. There were two choices. First step you may get nothing, nothing, or you may get 1, 1. Suppose the first step you got 0, 0. Then at the next step, if you had 0, 0 at the first step, for the second one, I'll put a little bit more than 50% chance of B2C2 being 0, 0, and a little bit less than 50% chance for B2C2 being 1, 1. Can you see that I made the second step depend on the first step? And if at the first step I got this as 1, 1, I'll change it in a different way. So if the first step I got 0, 0, then the next step will not be exactly 50-50 of 0, 0 and 1, 1. I'll change it a bit. If the first step was 1, 1, then the second step again I'll change it in a slightly different way. Can you see that I'm correlating all the particles? Okay. So if you mathematically try to write down, you'll basically have to do something like this. And after n steps of emission, if you see how many of these correction terms there are of order epsilon, there are 2 to the n correction terms. Okay, so that's huge, because now if you emit lots and lots of particles, and then there are 2 to the n correction terms, who on earth knows what the leading order answer will be? The leading order answer that Hawking got might be completely wiped out. Right? And then Hawking would have been creating all this fuss about nothing, because he would be right about his leading order calculation. But if the subleading order effects overwhelm the leading order calculation, then there was no puzzle to start with. Okay? So this is what people were hoping, because they didn't know any other way to solve the problem. Okay? So again, in schematic terms, the leading order answer was this guy was entangled with this guy was entangled with this. They came out in pairs, right? Each was entangled with his partner. But now they are subleading correlations. This guy is entangled with this, but also a little bit correlated with this guy. And why is that? Because whatever happened to that guy previously will affect the next guy. So now each guy is correlated with the other guy. So that's why I've drawn with these dashed lines. They are very small effects, but there are so many particles. There are like 10 to the 74 of these dashed lines for every one of the solid lines. Okay, so number of emitted quanta is very large. So now if you compute the entanglement of everything which is here with here, but take into account the little dashed lines, there are so many more of them compared to the diagonal ones, then maybe the entanglement of this with this is actually going down. It first goes up, but then maybe it's coming down, and then is there a problem? There will be no problem. Okay, so this was the hope. Okay, so they're assuming, so this is how Hawking leading order answer was, and then if you take into account the small corrections, you're hoping it goes like this. I put a question mark because you don't know that, but that was the hope. Okay, and if you could solve it this way, then there is no puzzle at all. Okay, so this is what led to this famous bet and its the settlement of the bet. So Stephen Hawking and Kip Thorne had taken a bet with John Preskill. These guys said that information is lost, and Preskill was a particle theorist. He said, I don't know how information will be recovered, but somehow it's going to work out. You know, it's going to be unitary, but I don't know how it's going to work out. So they took a bet. And then around 2000, Maldacena wrote a paper saying that these kind of small corrections should fix the problem. Okay, there are so many of these terms. We just saw the argument, right? That they should fix the problem, though he didn't do anything else with it, but he made the comment in that paper. And then 2004, Hawking had been hearing a lot about this and other papers in ADS CFT, and Hawking said, okay, I think I basically agree with you. The small corrections could fix the problem. He put it in a different language. He said that there could be a subleading saddle point. A saddle point is something you do in the Euclidean theory, but when you finally see what it means in the Lorentzian theory, it just means a small correction. If you have a subleading saddle point, it makes small corrections to the actual state. So it was the same argument as Maldacena, but couched in a different way. Subleading saddle points are very, very suppressed, because this saddle point has an exponential action. It's very suppressed, but we are looking for a small effect because we have this large number of particles. We are so happy with 10 to the 74 particles that if the effect is 10 to the minus 74, we'll be all good with it, right?
Starting with these small corrections, the the fact that they could potentially resolve this paradox is to be attributed to whom?
So I think the time, people have been thinking about it off and on for a long time. Even older papers of Parekh and Wilczek, they tried to argue that if at one step you emit a particle, as compared to not, like you have a 0 or a 1, then the mass of the remaining hole is slightly different, right? Because you lose it or you don't lose it. So the temperature of the hole, which depends on the mass, is slightly different. So next guy comes out at a temperature which depends on the temperature, whether the previous guy had an emission or not. So there are slight correlations. So people are looking for correlations between different particles of Hawking radiation all the time. But nobody said this will bring the page curve down. I think Malthussen's paper was the first one we sort of tried to say, and that's also in the discussion section. It wasn't the goal of the paper.
But that is an internal black hole.
It was, yeah.
So,
But the argument was about the normal black hole, the page curve, because he was trying to solve the Hawking puzzle. It's just a comment at the end of in the discussion section. There's a couple of paragraphs.
So I think Wittgenstein,
Okay.
around if I remember, around 94, I have to go back and their argument is similar about adding bits, what is it? Taking quantum bits and seeing how to build up a black hole.
Yeah, that I know. Yeah, so how to build up is slightly different. You can take quantum bits to build up, and later, Tuhft also did a lot of stuff with that.
So I have to, it has a long time ago since.
Okay.
I have to go back and see whether they are also talking about whether the larger effect can sort of
Okay. Yeah, so yes, there could well be other people who also said this, so I don't really know. And
I just remembered because then they asked who did it.
Yeah. So I also don't know who did it first. I just remember that it started off in the string community with this paper of Malthussen.
Maybe lots of other.
Yeah. So correlations between Hawking quanta are definitely going to be there, but whether they do anything is the question, right? Whether they bring the page curve down. Okay. So then Hawking started thinking that maybe this works because too many people in string theory were telling him that it might. And so he surrendered the bet, which was a bunch of sports encyclopedias, and he paid it off to John Preskill. But Kip Thorne refused to surrender because he said, look, you haven't told me how it comes down. You're just making some vague argument that you have small corrections, so on. Show me something, right? And in fact, this became a split between the string community and the GR community. In the GR community, nobody believed this stuff. They said, if you have entanglement growing like this, if you have small correction, it still grow approximately like that. Maybe there's a small change to the growth. And the string community guys were saying, they all came from the particle physics background where everything is unitary. So they said, oh no, there are so many terms in the expansion, it will change over, it has to come down, this must be the answer, we won't worry about the puzzle. Okay? So it's sort of roughly split down among the community, two different communities, but as it turns out, in this case, Malthussen was wrong, and therefore Hawking was also wrong to go along with him. He surrendered the bet in 2004, because we'll see that none of these people actually sat down to write a model. That's like we actually tried to write a model on the previous slide. We wrote a model for the small correction do. How do you correlate them? We said, okay, if you have 0, 0 at this stage, at the next stage, let's have a little bit more or a little bit less of this. You got to write down something. So you should at least write down a toy model, even if you don't know what numbers you want to put here, because you don't know what quantum gravity is going to actually give rise to that. If you have, let's say, want to put 100 particle pairs, you should put some epsilons of the order of, maybe 1 over 100, and show that if you do that, then the page curve will actually come down. But no one did that. They were just talking about it all the time, but no one even tried to write down one toy model. Okay? So this split between the GR and other community, this split here, this guy not paying up and this guy paying up continued. And then it turns out it's not possible. The page curve doesn't come down. It doesn't matter how you choose these epsilons, the page curve will never come down. So that argument is actually fake, but this also proves that the Hawking original argument is completely robust. Because Hawking did a leading order calculation where he just said, okay, I just get this pairs and I'm not going to worry about any other subtle corrections. But if we look at all the subtle corrections possible, we don't even say where they're coming from. We put arbitrary epsilons anywhere you want. And if with that, the page curve can never come down, it means that any small quantum gravity effect is not going to help you. If the black hole horizon looks like this room to leading order now, to leading order, there can be any small corrections anywhere, you can't save the information puzzle. So that makes the Hawking argument much more precise, much more solid, and something you really have to worry about, because now either you change the black hole structure all the way to the horizon, which is a big change because the horizon is such a classical or semi-classical region. It doesn't look like there should be any quantum gravity occurring at 3 kilometer length scales. Either you do that or you lose your quantum mechanics. Now this makes it into a rigorous theorem. Okay? So then we package this into the context of something more precise with all the metrics and so on. You can put epsilon deltas everywhere, and we make it into a rigorous theorem which says that, which I'll give you at the end, that if you have the horizon we can make it precise what these words mean, but in words, if the horizon behaves like this room to leading order, there is no solution to the information puzzle, you will lose quantum theory. Okay, so what we have to do is we have to now see, let's just take the remaining 20 minutes I have, and let's see how you actually show that the small corrections will not help. Okay. So a little bit of history of this. At around 2009, I was giving some lectures in CERN, and Witten was visiting CERN at that time, and then he wrote me an email saying, look, the small correction will fix it. Everybody's saying so, looks so obvious. Why won't it work? So I kept on drawing these pictures and showing, look, the entanglement will keep going up. Why are you worried so much about it? We exchanged emails for almost 6 months, and he wouldn't somehow understand what I was saying. We just couldn't communicate. So I said, okay, let me make a rigorous proof. So then we made the proof. And so now, of course, it's understood this is how it works. But the important thing is this proof uses a property of entanglement entropy called strong subadditivity, which many of you may have heard of. But the point is, strong subadditivity property of entanglement entropy has no elementary proof. Okay, it's the only theorem which you can find in the textbook of Nielsen and Chuang, which can't be proved in one page. It requires a 10-page appendix and then a 5-page proof in the bulk of the book. It has no intuitive proof at all. Okay, so that's why the intuition which comes from the small correction theorem wasn't easy for people to grasp, because it almost looks like a logical argument. You put small correction somewhere, why can't you change it? But the fact you can't actually requires the power of this strong subadditivity, which was a theorem proved around the mid-1970s, if I remember right. So it's a very non-trivial theorem because it's just about quantum entanglement of a finite number of things. All the elementary theorems about it were like clear way in the beginning of quantum mechanics. This is the only guy which came like 1974. So we have to use the power of that, but of course the theorem is there, and Lieb and Ruska, and so we just use that, and now we can prove this, and that will make the Hawking argument robust. That's going to be very important for everything, because that tells us we've got to change the black hole completely, and as you saw from the colloquium, that's what string theory is telling us through fuzzballs. We need to understand that. Okay, so let's try to make a model of this. So I have just about enough time to finish this. Let's try to make a model of this. So you remember these slices, this is r equal to 0, this is r equals 2m, this side is r equal to infinity, space-like slice looks like t equal to constant here, looks like r equal to constant here, this particle is entangled with this particle with this, and so on, and then a new pair is created here. And here the physics is close to normal, so this particle pair will be like 0b, 0c plus 1b, 1c plus a small correction. That's what the whole physics here is. Is that comfortable to everybody? Setup is clear? Okay. Outside at flat infinity, we assume physics is normal. This is just like a particle gone far from the black hole, so nothing new happens here. Inside the black hole, these particles have been inside for a long time. Actually, everything is normal here. This is r equal to m. There's nowhere near r equals to m. It's a completely smooth region of space. So we are entitled to assume that physics there is also normal, but we won't need that. So I'm not even assuming that. I'll just say I don't even know what happens here. Okay. All I'll assume is that physics all around here is unitary. I mean, whatever happens is satisfying the rules of quantum mechanics. But anything inside can happen here. Maybe these particles reshuffle with each other. Maybe this guy goes and does things here, which are not supposed to happen with smooth physics. But this is, I don't need it for the theorem. I just blanked it out saying, I don't even claim what happens here because I don't need it. I just need to know the horizon is a normal place for the production of the next 1 or 2 pairs. That's all I need to need. And these guys are normal, so they are completely normal. Nothing happens to these guys. Once something leaves, it leaves. This is the setup. Any questions about the setup? So just the Hawking puzzle repeated, and now we want to put in the small corrections. So this is just again repeating what we said before. If physics is normal around the horizon, the modes will stretch. The 2 oscillators were closed, then they become far, so a particle pair will be created. I'm just repeating what I said before. Okay. So this is just some notation. This particle is called B1. You remember this guy was called C1. This is B2. This was C2. Let's say there are n of them, so this is Bn, this is Cn, and the new pair will be called Bn plus 1, Cn plus 1, that's the new pair. Collectively, all the older guys, B1 to Bn, at step n, I have n of these guys, I'll sometimes just write this curly B for it. Is everybody comfortable with the notation? Okay. So what is the entanglement? So entanglement is of everything outside with everything inside. Let's put the boundary at, let's say, 10m, somewhere sufficiently far from the hole so I don't get confused with the hole. So I want the entanglement entropy of all of B1 to Bn, which is schematically just called B, with everything inside here, right? The normal symbol for entropy, entanglement entropy is S of A. A is the set whose entanglement you want. So if you want the entanglement of these guys, you will write S of the set B. So these guys are entangled with this, right? We said if there were 3 guys here, there are 2 to the 3, 8 states here. They are entangled with 8 states over here. but I want the entanglement of this set with this set. That entanglement is called S at step n. Entanglement at step n is the entanglement of these guys with everything else, and everything else over here. So it's still just notation, we haven't done anything. Okay, we're just setting up notation. Okay, so now what happens at the next step? We had only n guys here, we had this and this on the previous slide. Now this system, which is all still inside R equals 2m, R equals 10m, it slightly expands and creates one new pair. You guys remember the new pair was called Bn plus 1, Cn plus 1, one new pair. But all this evolution is actually unitary. Whatever happens here is some complicated unitary stuff going on in there. It has nothing to do with these guys right now. And this is a general theorem. If we have two different systems, and this is entangled with this with some entanglement entropy, if one of them undergoes some unitary change among itself, the entanglement of this guy with that guy cannot change. So you can roughly see that if you have state 1 times 1 prime plus 2 times 2 prime, entanglement is log 2. You can rotate these two states or do anything else to it as a unitary change, but still there will be two terms. Psi 1 will go with some chi 1 prime now, and psi 2 will go to some chi 2 prime now. But that's a unitary evolution, the entanglement doesn't change. So at this step, the entanglement of the outside with the inside is still S of B. It hasn't changed. It's just a trivial statement, nothing has changed. But now let's start looking at the values of the entanglements. The new pair I got, you remember it's called 0 Bn plus 1, 0 Cn plus 1, 1 Bn plus 1, 1 Cn plus 1 in Hawking's leading order answer. In the leading order answer, what are the entanglements of various pieces? So Bn plus 1 is actually just entangled with Cn plus 1. Can you see that? This, you can think of the spin up, spin down, plus spin down, minus spin down. It's like a singlet state. So B and C are forming what is called a bell pair. It's like a spin up, down, minus down, up. It's just a singlet. So if you compute the entanglement of B with C, B is only entangled with C in this leading order Hawking calculation, and the total pair B and C, that's in a unique state. Do people agree this is a unique state? 0, 0 plus 1, it's like the singlet state of two things. That can't entangle with anything. If something is in just one state, that system can't entangle with anything, because to entangle with something you have to have at least two states. State 1 times some other state plus state 2 times some other. If something has a unique state, it can't entangle. So the entanglement of this set, remember the notation was if I write S and some set of particles, it will be the entanglement of this set with everything else. But this guy doesn't entangle with anybody, so that entanglement is 0. If you just look at the picture, this new pair just came out of the vacuum. So they are just entangled with each other, like they may make a singlet with each other, but they are not entangled with either this or with this. Okay? So very trivial statement, the entanglement of this with everybody is 0. What's the entanglement of just Cn plus 1? Well, C is entangled with B. You can see that C is 0 when B is 0, C is 1 when B is 1. You can see the entanglement of that is log 2. Again, very obvious statements. Okay, up to now everything was exact, so I was repeating what Hawking was telling us. Now let's put in the small corrections. So if you put in small corrections, slightly change the state. I didn't put the details of like add a delta psi and change it, but if you make a small change, all that happens is the entanglement of this pair, it need not be 0 anymore, but it will still be small. So it will be less than some number epsilon 1, where epsilon 1 is much less than 1. I'm just putting in the fact it is small. Okay. Also the entanglement of Cn plus 1, it was log 2. It can change a little bit, but can't change too much. So it may reduce by some amount epsilon 2, but can't reduce by more than that. So it's bigger than log 2 minus epsilon 2, but epsilon 2 itself is quite small. I'm just putting in the small corrections. You can do this more explicitly by writing a state and doing it, but these are expected. Whatever state you change, this is what you will get. Okay, so now let's go to what we are really interested. What's the entanglement after one more particle has been emitted? You see, we already had these particles emitted. Now one more guy is emitted. Now I want the entanglement Sn plus 1 is the entanglement of all these guys with everything else. So what is Sn plus 1? Just by definition, is the entanglement of the set B plus Bn plus 1 of this set with everything else. That by definition is what you call the entanglement of the outside with the inside at step n plus 1. See, almost nothing has happened so far. It's all just still definitions, right? Okay. And then the entire proof is in one slide. So we'll have to go a little bit slowly through this, but this is the end of the story. Everything was just definitions. So now what is the strong subadditivity theorem? Suppose you have three quantum systems, A, B, C, and there's also a fourth quantum system, D. And they're all entangled with each other. So like so far we're just talking of two electrons and they were entangled, spin up, down, minus, down, up. But you can have very complicated things where you have like three guys are entangled. It could be 0, 0, 0 plus 1, 1, 1, right? You can entangle three things like that. Or you could have four systems all entangled with each other. This theorem is pretty non-trivial because you have four systems entangled with each other. We'll actually talk only about A, B, and C in the inequality. If you take the entanglement of the set A union B, whatever is here and here, with everything else, which means with C and D, that's called S A plus B. Now if you take the system B plus C, and you compute the entanglement of that with everything else, and everything else means A plus D, that's this number. And the inequality says this is bigger than the entanglement of S of A. S of A means entanglement of A with everything else, which means A entangled with B, C, and D. And S of C, which is C with everything else, which is A, B, and D. This is the actual inequality. Okay. If you actually don't have a system D, it actually becomes somewhat trivial. You can prove that. So the D is also important to this inequality. If you want a physicist proof of this, which is not a real proof, but which is at least intuitive a little bit, Kalyan Rama from Mad Science, he wrote a small paper giving an intuitive proof. The intuitive proof he wrote for the case where there are up to 2-point correlations and 3-point correlation, but no 4-point correlations among the bits. It turns out the non-triviality is because there can be 4 and higher point correlations. Okay? But just for simplicity, if you assume there are no higher correlations, you can make a physicist proof of this. But again, it's not a real proof. But if you just want to play with it, you can read Kalyan Rama's paper. Okay, so this is the theorem. And so this we are just going to use. We don't derive. This is all the hard work is of Ruska and Lieb. And now let's see. The system A, B, C, I can choose whatever I want from my this system set B. I'll call that my set A. Do you guys remember what B was? B was these bits at the previous step. This was set B. So the players in the game are the set B, Bn plus 1, Cn plus 1. Okay, these are the players in the game. The set B will just be the single bit Bn plus 1. The set C will be just a single bit Cn plus 1. Recall S, the entanglement entropy at step n was just S of B. These are the guys outside, entanglement step n plus 1. Entanglement step n plus 1 was S of B, and the Bn plus 1 has also joined the outside. So entanglement of this set with everything else is what you would like to call the entanglement of at step n plus 1. What else do we know? I'm collecting all the information from the previous slide. The entanglement of this particular set, which is union of B and C, it was small because in the leading order it was 0. They were just entangled with each other. And the entanglement of set C plus 1 with everything else at leading order it was log 2, but now it can't be too much different, so it's bigger than log 2 minus epsilon. Okay, we have defined sets A, B, C. We have a little bit of information about them. Let's plug it all back into this equation. Okay, so sets A plus B. A is just this set, B is this set, so you can see I put this here. Here B plus C. B plus C is this and this, so you can see I wrote this. Here's S of A. A was just the set B. Here's S of C. C was just Cn plus 1, so you can see I just copied in all the guys. Set B plus Bn plus 1, that is entropy of this is Sn plus 1, so this is Sn plus 1. Okay. And now let's look at the inequality. S of B is what we call Sn, so I get the Sn. And then if you just move the pieces around by just using this and this, you find this answer. Okay. So what has that told us? It told us that if we just have small corrections, it doesn't matter how many particles are there. You can just go step by step. But the entanglement at step n, whatever it was, at step n plus 1, the entanglement has to be more. It increases by log 2, which was Hawking's answer. It can become slightly less, but only by this tiny amount. So if your correction was 10 to the minus 74, this will be 10 to the minus 74, still going up. Hardly makes a difference. The fact that there are 10 to the 74 particles which are going to come out, it never helps you. So you never actually end up finding the product or number of particles with the smallness of the correction. But they were trying to balance the two things against each other. It doesn't work like that. You can just actually get the smallness at each step is all that matters. And this was the intuition of all the GR people. Like when Kip Thorne wasn't agreeing, he was saying, well, at each step you're getting log 2. You make a small change, it will be log 2 minus a little bit. What do you mean it will come down? And the string people never checked anything. They never even tried to write anything. All the things we wrote here, they never wrote anything on the piece of paper. They said, oh, it will just do something complicated, it will come down. Okay? But it doesn't come down. Okay? But it's not easy to see this because this theorem itself is very hard to prove. Okay? So that's why it's not intuitive, but that's where we are. So let's see what we can make. Putting this together with all the GR in it, you can make the following exact theorem. So the Hawking 1975 argument, you can now convert into what I could call Hawking's theorem, and it goes in the following way. If you assume the physics at the horizon is like the physics in this room to leading order, it's very important now I use the word leading order because these guys were all saying there'll be small correction. The whole fuss was about small corrections. I only lead to leading order, and two quanta far from the whole are independent of the whole. So once something leaves, I'm not going to change it. Because these days people are also talking about the fact the hole could magically reach out here by a wormhole and flip the particle. And I think it's all nonsense, but people talk about that there could be some wormholes that go out and flip the particle after it's gone, millions of miles from the hole. Looks like science fiction to me, but right now we are assuming it's not there. Let's do the theorem for what the theorem is worth. So with that, this is the other assumption. Then there's no solution to the information problem. So you can put all the, in the actual paper you can see more details of what we actually mean by leading order and so on. So we made all that precise. But this is the content of the theorem. And so in other words, the same statement restated, lead a correction of order unity to the low energy physics at the horizon. It can't be like this room. So if this was the Hawking process graph, the actual graph can only go epsilon down from there. It can't actually turn over. Okay? So you can see how serious this is, because Hawking's puzzle was always bothering us. But it wasn't bothering the string theorists because they were living in a kind of fake world where they thought the problem would be magically solved by small corrections. But it wasn't true. But this confusion ran through, first Maldacena and then Hawking himself accepted the argument, and then Whitney was having the same confusion. But a lot of other string theorists actually had exactly the same confusion. But somehow none of the GR people actually believed this. So it was really a community split. But they had really been playing with the pair creation explicitly for a long time. While the string people had never actually played with the pair creation, because particle creation curved space is not what string theory people do. They come more from the particle physics background and they never actually do this calculation. So it wasn't in their intuition. But interestingly, the GR people were not saying this at any step. But when you actually work it out, the GR people were correct here. And so what's the way out? So we are, yeah.
So I thought the point of the small correction was that it will also be multiplied by some very large factors.
So the point is, they hoped it would be multiplied by the large factor if there are many particles. And the point of the theorem, it doesn't get multiplied by the large factor. That is, if you actually put small correction at every step, and you actually work out what happens, you never get a term where the small number is multiplying the big number. That was the mistake.
So I think maybe they were hoping that there would be an n next to the x.
That's exactly right. And if you open up Nielsen and Chuang with all the inequalities, and you just have two systems correlated this way, you go through, there are many, many inequalities, right? There's a Holliver bound, there's a Hopdeva bound, there's so many bounds. You use any of the other bounds, some power of n always gets in the story. Some power of n always gets into the story. You get n times epsilon in all those bounds, sometimes root n, sometimes n to some other power. Okay? But if you go through this particular inequality, the strong subarbitrary, that's the only way you get a bound which doesn't involve n, because you're looking very hard for a bound which does not involve n, because once it involves n, you really can't make any argument, right? Because n is huge. You can just choose epsilon to be order whatever it was. Even if it's root n, it doesn't matter. N is a big number, small corrections and you are through. You're looking for a bound that doesn't involve n. That's exactly the point. And if you use this inequality as opposed to any of the others in the entire area of inequalities among, you will always get some n bothering you here. And if I had an n here, there was no argument to make. Maldacena would have been right. Hawking would be correct to give up. And there was no puzzle to solve. Okay, because then some quantum gravity effect, someday we'll find it, but who's going to find it someday? Small effect could come from anywhere.
Is it right to think that every emission is maximally entangled and that's why this is going up?
That's exactly why it's going up. And all we have done is we made it a little less than maximally entangled by putting the epsilon. But the point is that I think the intuition which was slightly going haywire with people was, they thought that suppose I have a particle pair, they entangle with each other. Now entangle them a little bit less with each other. But then if suppose there are a million particles outside this room, I can entangle a little bit with this, a little bit with that, a little bit with that, and then I can make some very crazy interesting stuff. The point is, if you just sit and think about it for 1 second, it doesn't happen. How do you entangle this guy with lots of guys? Suppose this guy has two states, up and down. Okay? So you can take state up times something there, little bit of something there, something else there, something else there. There are a million states to choose from. But in the end, what does that mean? It means you get this guy times that particular linear combination which you just took there. So it's actually only one state. There are a million particles there. But if you take this time something plus this time something plus this time something, you factor this out, all you get is some particular one vector over there. So if you had spin up and spin down, you get spin up times some one vector out of that million dimensional space plus spin down times some other one vector out of the million dimensional space. The fact that space has dimension 1 million is completely irrelevant. So you can't entangle something by putting small subtle things and make anything interesting out of coupling to a lots of guys. This is where the intuition was going wrong. So if you actually just start writing it down properly using a bit model, you can just see it doesn't happen. Okay? But nobody ever wrote it down. Yeah.
You wrote down these Bell type states. So have you ever tried writing down some other entangled states? It is useful.
Yeah. it makes no zero difference. So for example, my student Steve Avery wrote it with all 4 states. He said the entanglement is not just 0, 0 plus 1, 1. You can take 0, 0 plus 1, 1 plus 0, 1 plus 1, 0. Okay, then you get instead of a 4 by 4 matrix, you get a 16 by 16 matrix. It makes no difference because whenever you see these epsilons, you'll get epsilon by 4s. The argument is the same, or 4 epsilon something. It doesn't make any difference. But you can play with that. You can make absolutely anything. It's just that you need a finite dimensional space of the low energy physics there, which you have in the Hawking case, just a finite dimensional space. You can have 2-dimensional, 4-dimensional, depending which spin particle you have.
I have another question. So, consider this particular slice just
This one?
very near to the horizon, leftwards.
Yeah. Oh, to this side? Leftward means here. That's not.
The horizon.
Okay, those are rightwards here. Oh, just to the left of it. Yeah, good. Yeah.
And now the particles are created somewhere, but when it is created, because it is shrinking, like the black hole is evaporating, it's shrinking, so the horizon processes it. So
Okay.
both of the particles go out, right?
No. So what happens is it doesn't cross it because as the thing is evolving, these guys are also not staying where they are. So let's go back to the metric of the black hole. Okay, you're saying if the horizon shrinks sufficiently fast, something can go out. Okay. It doesn't actually make. Okay, so let me answer the question in this way. The horizon is actually shrinking very slowly. And so because of that, these particle pairs which are inside, they are falling in. Remember the geodesics inside are going in, right? So they are going in at a very quick rate. And so you're going in more quickly than the horizon is coming in. So in principle, it is true that when the black hole is shrinking, instead of event horizon, you define something called the apparent horizon. And the apparent horizon is actually shrinking, right? When the apparent horizon is shrinking, it is actually possible to be inside the horizon and then to get out. You can be inside the apparent horizon, you can get out exactly by shrinking. But the range from which you can get out is an exponentially thin band around the apparent horizon. Because the rate of evaporation is so slow. So it depends on the rate of evaporation. So only something very close will get out. But these guys have fallen in very deep. I mean, we haven't seen that in the pictures here, but they have fallen in there very deep. And so that's not language, because they're keeping on falling in, like the light cores go in. So every time one more particle goes out to reduce the horizon a little bit, in that much time the guy which was inside has gone further deep into the black hole because the geodesics were going in. So this picture is not going to make it clear. But to do that, let us write the full metric of the evaporating black hole in what is called a Penrose diagram. So do you have any idea of the Penrose diagram? You've seen those things? Yeah. So the Penrose diagram from the evaporating black hole, now this is only for people who know this, and if you don't, it's fine. You don't lose anything if you don't focus on this part of the discussion. This is the Penrose diagram of an evaporating black hole made by some shell of matter coming in. This time the black hole is also evaporating, so I've allowed the evaporation. The event horizon is here. But the actual surface, the trapped surface which you have actually goes like this. So there's a line which is not light-like, but slightly curves like this. So there are guys here which were first trapped inside this horizon, and now they can go out. So this is the narrow band where the stuff which you are talking about happens. On the other hand, the slices which I am drawing on this diagram, they actually look like this. And the pair creation particles are this entangled with this and this entangled with this. Okay. It's not here. Okay. So those things are not clear if you just draw schematic pictures. But people have done this. For example, what I was referring to is RST model. We do the Russo-Susskind-Thorlasius model in 1+1. So they solve this evaporation with this curve exactly, all the feedback put in of the evaporating hole. In that hole, you can actually compute all the slices, you can compute the entanglement, you can see it's going up. So the full page curve has been reproduced for this 1+1 quantum gravity with the full feedback and the Hawking entanglement calculated. So if you want, you can see those papers. It doesn't make any difference to the ideas. Yes?
So here we are assuming that whatever the particles are outside the band, they are not interacting, their states are.
They are gone. Yeah, they are just like photons that came out of a piece of coal, they are done.
But if we assume that there are interaction between those particles.
Okay, between each other will make no difference. The particles go out, if they interact with each other, it makes zero difference to the argument, because if you have two systems A and B, and you want the entanglement between them, as I said, any unitary evolution of this system by itself, you can make. Any unitary evolution of this system within itself you can make, like interact as much as you want, but the entanglement of this guy with this guy will not change. So if I take one electron here, one electron on Mars, and they are entangled in a singlet with log 2, up, down, minus, down, up, I can take this guy, I can spin it in a circle like as much as I want, and I can take that guy, I can spin it around as much as I want, change the state completely, but the entanglement between this guy and that guy will remain log 2. So because of that, but if somebody says there's an interaction between these guys and these guys, so now they are millions of miles away, but suppose somebody were to say that, that can change things, right? Because this is entangled with this, and somehow if you say this particle can magically come out, for example, then the guys outside entangled with each other and not entangled with the guy inside. And there are people saying all these things. I mean, if you want to listen to all the nonsense going on, there are people saying all these things. Okay? So there's no shortage of that kind of stuff going on. The one only outside to outside? Yeah, so that's an elementary theorem. You can find it right in the beginning of the text, that if you have systems A and B, if you apply a UA, unitary only to A, and a UB only to B, the entanglement will not change. Yeah, so that theorem is absolutely there. It's right in the, maybe the first chapter or second chapter of Niels Hachon. You can find it, yeah.
Sorry, off the record, just to clarify, the nonsense that you're talking about refers to this EI to DPR.
That kind of stuff, that kind of stuff. This is called the A equals RB models and all this kind of stuff. So they don't actually have a uniform thing which they say, but sometimes they will say, this is what happens and things come out. So it goes back to the original paper of Susskind and Maldacena, the cool horizons. They draw these wormholes. But then you have to ask, what do the wormholes do? So some guys say the particles actually come out. Some guys say because that, twisting this guy here will change something there. So all kind of things have been said. I don't think they make sense. But we have to put everything on the table here. So yeah, people say all that, yeah. It's called the A equals RB models, yeah.
So what is with this inequality?
Pardon?
The inequality, for the equality.
Yeah.
So that's not proved, you were saying, right?
That's not what?
What is the argument, in this case, why are you starting from this point?
Why am I starting from here? Yeah, I just pulled it out of the blue right now. I just put it out because I knew that I wanted to get the entanglement at step n+1 of this compared to the entanglement of S at step n, which was this. So I just have various particles, they all entangled with each other in a certain way. Then I just want to know if I can find any inequality between them which will help me. So I'm looking for inequality between Sn+1 and Sm. That's what I'm really looking for. Then I just open the textbook and I go through everything to try to find anything which can help me. And there are so many inequalities. Right now I just pulled it out of the hat and just put it there. So there was no motivation. But clearly it gets me to something which I want. Yes.
So in essence, we are looking for a counter.
No, I
Pardon?
think they're asking, this is the strong subadditivity theorem. I mean, this is what the statement of the theorem is.
Yeah, this is always true, and this is the theorem, that if you have in quantum mechanics, if you have any four sets A, B, C and D, whose degrees of freedom are independent, that's also important. They're independent degrees of freedom. So 4 different boxes which are entangled, but it's not like this bit is partly there or something. Then if you compute entanglement of the bits in this way, this is what you will get. So it's just an abstract theory, quantum mechanics, nothing to do with black holes, nothing to do with anything. We're just going to use that.
So we are looking for inequality that does not have any end.
That's exactly what we're looking for. If it depends on the size of the system, many of the inequalities depend on the dimension of the system. Then it's of no use to us because dimension is so big. If that n came, let's say here, or even root n came here, like comes in many bounds, then anybody could say very small epsilons will take care of it, and then there was nothing to say. No Hawking. Pardon?
What's the rule of system D?
What's the rule of system D? Yeah. So it turns out if there is no D, if you have only, let's say, A and B, 2 systems which are entangled with each other, then the entanglement of A, S of A, is actually equal to S of B. Because how much A is entangled with B is also how much B is entangled with A. Like if there are 2 electrons, this is entangled with this, but then that's entangled with this, both are log 2. So suppose D is not there, then S of A is equal to S of B plus C. Right? There are 2 systems entangled with each other. If you use that, then S of A plus B is just S of C, which is same as this guy. S of B plus C is just S of A. It's a triviality. So if there is no D involved, the theorem immediately degenerates to an equality. Right? So the point is you do need 4 systems. To make it non-trivial, you need D. Right? And so if you go back to the physical case, where was D? There's a lot of other stuff here. See, these guys are partly entangled with this. I used this was called A, this was called B, and this system was called C. Right? But then, yeah, they're not the same.
Just to play devil's advocate, so I think the one, so this is kind of like this argument of reciprocity for the Libre Hilbert proof, for instance, is for finite dimensional Hilbert
Yeah.
spaces, right? So for instance, if you have quantum field theory in your space, and then you have to always worry about whether ultimately you have to worry about gravity and so on. So is there a precise statement of this form?
Okay, sir, again, I didn't
So
completely.
I'm saying that the strong subadditivity proof that the statement that you had is for finite dimensional systems.
Yeah.
Right. So, but on the other hand, Hawking's calculation is really for a field theory. So,
Right.
and ultimately, then you have to worry whether that you can approximate it with some cutoff, etc., during some process, some stage of evaporation. But eventually, when you finally the whole
Yeah,
thing-
it's worth worrying about.
Yeah.
So we spent some time trying to take the exact field theory and then to reduce it into the degrees of freedom we are worrying about, which are all quanta of the wavelength of Hawking radiation, and then separating out all the high energy degrees of freedom which don't participate in anything.
Yeah, this is the
Yeah.
effective.
Yeah. Okay, not in that effective. This was just in this context itself. We look at all the high frequency guys and we try to see what those guys do. And you can then just keep putting bounds on that because the high frequency guys don't actually produce any Hawking radiation. They all go by the adiabatic theorem. And so with putting...
So there is some implicit assumption that quantum field theory in curved space is, somehow there is what we call bulk effective field theory has to consistently hold throughout this process, and then you can apply the same Hilbert space
Yeah.
throughout the page,
Right.
lifetime, etc. Right? So
Yeah.
those kinds of things. I mean, at least, I don't have a sharp counter argument, but at least I can sort of imagine that maybe there is.
No, so you should absolutely worry about that. That because of field theory, you have to worry about the fact that we are just using the few quanta which are actually showing up in Hawking radiation. Like Hawking radiation, a quantum comes out, the other quantum comes out. Rest of it is all the vacuum. So what is all that vacuum doing, right? But because there are no quanta there, they can't entangle with anything. So but you're right. You have to start with the full thing. As for example, we worried about the fact.
Another way of saying thing is that these the spins that are coming out in what Hilbert space are they really living is a kind of a complicated question, right? I don't know whether that's so.
Okay,
clear.
so let's try to talk about that. So that question has to do with gravity. Even in this room, there's quantum field theory, and suppose I have an electron here. So that's the extension of the quantum field, right? And maybe another electron here. And if you go over to the condensed matter people, they will just be computing their entanglements, right? So even at this level, you could ask, the field theory is there. There are all the divergences in the field theory and all that. In the end, how can they just say the entanglement of this spin with this spin, the 2 qubits they are using to make their quantum computers? What's the meaning of saying that's nicely log 2? So you have to go through the steps to get that. And so what are the steps you use to get that? You have to first look not at entanglement of sets, like in field theory you try to entangle a set with the remaining set. But then when you try to separate two parts of a line, there's always a UV divergence there. What you do is if you have a system here and a system here, you can define something called mutual information of this region with this region. If you do mutual information, then this intermediate part actually drops out and there's no cutoff involved. So in terms of mutual information, you can nicely go from the field theory description down to actually the bits that you use, because you're only doing low energy physics here. These are 3 kilometer quanta. But whatever I'm doing here has nothing to do with, you're right to ask how you go from the field theory to the quantum mechanics of the few particles.
Is there a statement of this that you can formulate entirely in terms of mutual information?
Yeah, so whenever I write the entanglement of something with something, as you said, this is just like I'm doing quantum mechanics for the quantum computer people in the lab, right? This, get rid of this. But you could ask that on the entire slice, there are degrees of freedom here which are not excited. What is happening to those guys? I think that's one way of phrasing what you are worried about, right? There are degrees of freedom everywhere in a quantum field theory. There are lots of harmonic oscillators everywhere, except that they are not excited.
Yeah.
There's just a vacuum. But what do we do with them? And that transition requires...
Hilbert space is living in. I think that feels.
Good, so let's ask that. So if you just open the standard QFT textbook, the Hilbert space will be, let's just worry about this because these are all gentle slices, the curvature and all doesn't matter. The Hilbert space we understand very well as the Fock space of 0 particles, the vacuum, then 1 particle, then 2 particles. That's the Hilbert space. So there's nothing subtle about it.
We know that it is not. Maybe we should have, this is kind of a more broader discussion.
Okay, yeah, we can happy to chat. Yeah. Okay. Okay. Yeah. Okay, if there are no more questions, I'll end. This is all I was telling you today. So what I'll try to do in the next lecture on Friday is that I'll try to tell you about fuzzballs and how we actually get the puzzle to be resolved in string theory. Because now you can see the only way out of this is that you have to change the inside of the black hole completely. So you have to see how that happens, because we said that's magical because the black hole is so big, how do quantum gravity effects go that far? Or if you still want to keep a smooth horizon, we should actually allow all possibilities. Then you need these magical effects that go from the inside of the black hole to these astrophysical distances outside, some non-local effects. So my personal belief is there are no such non-local effects, so I sometimes call those things crazy. But because many people do that, let's also allow that possibility. But now what we have learned today is that there are only two ways of solving the puzzle. Either you completely change the structure inside, or you introduce non-local effects that connect what's happening inside the black hole to things which are very, very far away. So how far away? The distance to which the radiation goes in the process of evaporation, but the radiation is moving at the speed of light roughly, and it's going to happen over 10 to the power 120 years. That's the evaporation time of a solar mass black hole.
You need interactions, right?
You need interactions. They're always entangled. That's always true for Hawking. You need interactions. So in 10 to the 120 years, light-like quanta will go to 10 to the 120 light years. So of course, you can make an even bigger black hole, then it'll have to go even further. So what would you really need to solve the puzzle? We also made some bit models to explain what they need. What you need is that across these arbitrary long length scales, if you flip a spin here, it would have to be able to flip the spin over there non-locally without light having time to go anywhere. Instantaneously, if you flip something here, it should flip the spin there. To me, that doesn't make sense, but that's the only possibility. If you don't do that, you have to change the horizon completely. And that's a strange thing to do. But when you start working with string theory, as we had seen, every time you try to make a black hole, that's what you get. That's what we call the fuzzball. So we'll do that on Friday.